Okay, so now we're going to talk about color selection. So this is sort of a overview of the next several slides. So in 2004, Spitzer was brand new, and some people in preparation for Spitzer's launch had done some simple theoretical models using the IRAC filters, predicting that young stars should be in this part of an IRAC color diagram, and YSOs of that sort should be over there. I'm going to show you that plot again in a minute. Buoyed by this success, then people were carrying on to the next steps. So, okay, well, here these objects are outliers in the IRAC color diagram. What happens when we include MIPS? So then we include MIPS in color diagrams to identify stars that are really red, in other words, young stars. As we got more and more data, we were able to notice patterns in where we were looking. So if you look at a field that's almost all extragalactic things, they're going to be foreground stars and then galaxies. And that's going to tell you something about what the colors of galaxies and stars look like. But then you can compare that to the color distribution of stars and star-forming regions, so to help you identify the young stars. The basic concept here is that you start to understand where objects should fall in any given color or color magnitude diagram by looking at things that you do understand before you expand it to things that you are trying to explore. So here's the earliest cuts. This is another version of the plot another copy of the plot from earlier. So I've got 3.6 minus 4.5 on the y-axis and 5.8 minus 8 on the x-axis. The photospheres, the stars without dust, are near zero color. You got class 2s, red in class 2s, class 1s. So she's made some pretty simple cuts here. So if it falls within this box, she called it a class 2. If it falls in this region of the diagram, she called it a class 1. But this was a relatively small field focused on, or really centered on one star-forming region. So as you start to explore bigger regions, you need to worry about whether or not the things you're looking at are really young. So this is 3.6 minus 5.8 on the y-axis and 8 minus 24 microns. So now we're bringing in MIPS on the x-axis. So we've got, again, stars with no dust, have zero color. Then we've got debris disks here that have a reasonably red 8 minus 24 color, but still a 0, 3.6 minus 5.8. So in other words, this is things that have like a ring of dust around them. And then class 2s are red, and class 1s are really red. The reason the Greek letters are there is because they're the names of specific stars that they were talking about in this article. So they wanted you to be able to easily see, where star named Delta was going to be in all of these plots. So this is now comparing a star-forming region to an extragalactic field. So this is K on the y-axis versus K minus 24 on the x-axis. And we've got Swire field, Swire studied galaxies. So there are nearby stars that have zero color and a range of brightnesses, and then galaxies, which are red and faint. So now we know what stars and galaxies should look like in this color magnitude diagram. Now we're going to look at a star-forming region. There are clearly lots of stars without dust, but then you can see this distribution of points looks really different than that. There's an awful lot of bright red things. Those are the young stars. There's even a lot of very red things, and those are young stars. That clump down there could be galaxies, could be young stars, we don't know. These are two much smaller fields that are part of the same Perseus molecular cloud complex. And here again, this is a star-forming region, so almost everything that we're seeing are going to be young stars. So even the faint red ones are probably young. But you can see this distribution of sources looks very different than the Swire ones. And same for NGC 1333. This is just another clump within the Perseus molecular cloud. And you can see there's a lot of red things, even red and faint things. So what color selection should you use? It depends on what data you have, where you're looking, and what you're looking for. If you're looking for debris disks, but you don't have any IRAC data, you can't really use IRAC to look for disks because you don't have any data. If you're looking for very young things like class 0s and you have lots of Herschel data, you want to use Herschel colors. So things start to get really messy because the regions of color space do overlap. And so you have to make educated guesses. You have to say, okay, objects brighter than this are more likely to be young stars than objects fainter. Like over here, objects that are fainter are more likely to be galaxies than objects that are bright and red. So you also have to use all the data that you can find, not just a couple of bands. And you want to be careful about what might fool you. So this is a WISE color diagram. So 3.4 minus 4.6 on the y-axis and 4.6 minus 12 on the x-axis. This was from a paper studying extragalactic things. And so they were very interested mostly in the galaxies. So they've got stars and elliptical galaxies, which are galaxies with old stars that have zero color. Then you've got things with varying degrees of star formation that are extending out and red. Right? So it's finding star formation. It's just not finding star formation in our galaxy. It's finding star formation elsewhere. And for them, T-dwarfs are noise. So they were just emphasizing the things that they found that were here are T-dwarfs, not galaxies. But you can see all of these objects here have colors comparable to young stars that are in our galaxy because it's star formation just in other galaxies. So for any given chunk of sky, there really could be a lot of things there. So this is plots from a friend of mine where she's just showing the diversity of stuff that you could find. So look at her axes. She's got 5.8 minus 8 in Vega magnitudes and 3.6 minus 4.5 in Vega magnitudes. But because she's an extragalactic astronomer, she's provided alternate axes, 5.8 minus 8 in AB system, 3.6 minus 4.5 in the AB system. Now, you can barely read this, but look at the diversity of stuff she's got listed. Quasars, submillimeter galaxies, blazars, SINGs, which are nearby galaxies, GLIMPs, planetary nebulae, large Magellanic Cloud carbon enhanced AGB stars, large Magellanic Cloud oxygen enhanced AGB stars, Cepheids in the Milky Way, Cepheus YSOs, in other words, young stars, white dwarfs, brown dwarfs, and asteroids. And they're all over the place. There's still some clumping, but there's a lot of things going on here. Here she's got 3.6 minus 5.8 versus 8 minus 24, and another diverse collection of, the stuff. So there's a lot of things that you could find. So you have to try to use all the information you have to make some good educated guesses. So yeah, you want to use data from as many bands as you can. You want to try to employ color cuts in more than just one diagram. You want to try to use your experience with other regions or other objects whose nature you understand, like most normal galaxies fall here, most quasars fall there. You're going to end up with a guess, which is sometimes not conclusive as to what the object is, which is why we keep calling them YSO candidates, not known YSOs. In my opinion, it's easiest to see this process if you use a big catalog, because then you can see more easily where most objects fall, so you can identify the strange ones. So you don't want to get 10 or 50, but you need, thousands of objects in order to see where most of them fall. So sometimes you're going to need to use the big catalog and sometimes not. So the color cuts we've talked earlier about are simple in that they're usually just one part of one diagram. But when you start having more data, you get more diagrams because you have more combinations of colors to use. And then you end up having equations that will tell you, okay, if it's above this line segment, keep it. If it's below this line segment, drop it, so that you can keep track of all the tests that any given object passes or fails. And bookkeeping all of this can be a challenge. So remember that equations that look complicated sometimes turn out to be really simple. So if you Google that horrible expression without the quotes, it will plot stuff for you, and you can see that that's really not too complicated once you plot it. So both the Gudemuth and Koenig approaches to finding young stars have collections of equations that look hideous, but all they are is describing line segments in the color, and color magnitude diagrams. So they're not so bad. Even if you just work through a few, even just with a pencil and a piece of graph paper, you'll see it's not so bad. It just looks bad. So when you're trying to do this for real, what you want to do is you want to measure the properties of each object in all the possible bands. Then you want to identify objects you understand and objects you don't understand. And if you're studying an entirely new region, the objects you understand might have to come from the literature, meaning like a different star-forming region. Then you can make plots and compare them in many different spaces. You can do this by hand, or you can let the computer do the comparison. Certainly when you're starting out, you need to work by hand. Then you have to make educated guesses and which objects are young, which objects are contaminants, keeping track of which objects pass which tests. So yeah, the bookkeeping can be a challenge. I do all of mine within the computer, but again, I'm not particularly using Excel. And you do have to be careful with limits versus detections, because limits are not the same as detections. And if you treat a limit as a detection, you're going to end up with some funny filters. You have to, indeed, the accounting is challenging. You have to keep track of which objects pass or fail. And you're going to have, in the end, at least 2 bins, possibly young stars and likely junk. There may be more than just 2 bins. And this cut is not going to be perfect. You're going to throw out some young stars with junk. But your success rate is going to be higher if you focus on the most likely to be young stars bin. You could spend a lot of time combing through the stuff in the junk bin, but it's going to take you a long time to find the treasure in amongst the junk. So then we're going to use all the data that we can to help weed down that possible young star bin.